Today, we're diving into one of the most powerful and, frankly, one of the most dangerous ideas in all of software, concurrency. It is the hidden engine that powers pretty much everything you do on a screen, letting your apps juggle a dozen things at once.
I mean, really think about that for a second. You're scrolling through a feed, a video starts autoplaying, messages are popping up, and new stuff is loading in the background. How on earth does your phone handle all of that at the exact same time without just completely locking up?
Well, that magic has a name. It's called concurrency. It's the art of structuring your software so it can handle many tasks at once. But it's a total high-wire act. If you get it right, everything feels incredibly smooth. But if you get it wrong, you unleash some of the most bizarre, catastrophic bugs you can imagine. So let's start with the most important rule of all.
Okay, before we go any further, we have to clear up a huge point of confusion. You'll hear the words concurrency and parallelism thrown around like they're the same thing. They are not. And really truly understanding the difference is the key to unlocking everything else we're going to talk about.
So here's the absolute critical point. Concurrency is about structure. It's how you design your code to deal with multiple things at once, even if it has to quickly switch between them. Parallelism, on the other hand, is about execution. It's when you are actually running multiple things at the exact same moment in time. And for that, you need the hardware to do it, like multiple CPU cores.
And this is the perfect analogy. Imagine you have one cashier. You can still handle 2 lines of customers concurrently, right? The cashier just switches back and forth, taking an order from one line, then the other. That's concurrency. But to serve both lines at the same time, well, you need 2 cashiers. That is parallelism. We design our software for concurrencies so we can take advantage of parallelism when we have it.
So, if concurrency is just about structure, why is it so ridiculously hard? To understand that, we have to go deep. I mean, all the way down to the bare metal. Because the real drama, the real chaos of concurrency, it starts with the physical CPU itself.
You see, compared to your CPU, your main memory, your RAM, is incredibly, painfully slow. So to bridge that massive speed gap, CPUs use layers of tiny, super fast memory right on the chip called caches. L1 is the fastest, and it's private to each core. L3 is a bit slower, but it's shared across all the cores. This whole system makes things fast, but it creates a new, massive problem. How do you keep all these little private caches in sync with each other?
The answer is a really clever but really complex hardware protocol called MESI. You can think of it as a set of rules where every little chunk of data in a cache gets a tag with one of 4 states. The first state is modified. This basically means this one core has changed the data, and it's telling everyone else, hey, this is the only true copy now. It's mine. Then you have exclusive. This is a lot like modified. This core still has the only copy, but the data is clean. It hasn't been changed yet, so it still matches what's in the main memory. Now this is where it gets interesting. We have the shared state. Just like it sounds, this means multiple cores all have a copy of the exact same data in their private caches, and they're all clean. They all match. So what happens when one of those cores decides it wants to change that shared piece of data?
And that is where our final state, invalid, comes into play. Before Core A can write to that shared data, it basically has to shout across the chip to all the other cores and tell them, hey, your copy is no good anymore, mark it as invalid. Their old versions are now totally stale. This constant chatter between cores is what keeps everything correct, but it's also the source of some of the sneakiest performance bugs in existence.
Which leads us to this absolute nightmare scenario called false sharing. See, data is moved around in fixed-size chunks called cache lines, let's say 64 bytes. Now, just imagine 2 completely unrelated variables, x and y, happen to land on the same 64-byte line in memory. Core A only cares about x and Core B only cares about y. They shouldn't have to interact at all, right?
Well, when Core A updates X, the MSI protocol kicks in and invalidates the entire 64-byte line for Core B, even though Y was never touched. So now Core B has to fetch the whole line again just to work on Y, which in turn invalidates the line for Core A. You get this furious, invisible ping-ponging of the cache line back and forth that can absolutely murder your performance, even though your 2 pieces of code have zero logical reason to interfere with each other.
Okay, so that's the chaos bubbling away at the hardware level. To tame it, we can't really control the CPU directly, so instead we have to move up the stack and use a toolkit of abstractions that our operating systems and programming languages give us.
And at a high level, we've got 3 main tools. A process is the heavyweight. It gets its very own, totally isolated memory space. It's super safe, but also really slow to create. A thread lives inside a process and shares memory with other threads. This is much faster, but it's also way riskier because one thread can easily mess up another's data. And then you have a fiber, which is an even lighter weight thread that's managed by the programming language itself, which gives us crazy fast switching times.
And that overhead, it makes a huge difference. A single context switch, that just when the operating system pauses one thread to run another, can take 1 to 5 microseconds. Now that sounds like nothing, right? But if you're a web server trying to handle tens of thousands of connections at once, those tiny little delays stack up and create a massive bottleneck. And that is exactly why these low overhead tools like fibers are such a game changer.
Now, the most fundamental tool for managing all this shared data is a lock, and there are two main flavors. A mutex is a sleeping lock. If a thread tries to get the lock and it's not available, the operating system puts it to sleep. This is great because it frees up the CPU to do other work. A spin lock, on the other hand, it's a busy wait lock. The thread just sits there in a tight loop asking, is it free yet? Is it free yet? Burning CPU cycles the whole time. It's really wasteful, but it's faster if you know the lock will only be held for a nanosecond.
So, with those basic tools in our toolbox, engineers have built bigger, higher-level patterns. These are like architectural blueprints for designing large-scale systems that are safer and way easier to reason about.
And one of the most powerful is the actor model. The core idea is simple, but it's totally revolutionary. It asks, what if we just got rid of shared state completely? In this model, everything is an actor. Each actor has its own private data that nobody else can touch. The only way they can communicate is by sending messages back and forth. No shared variables, no locks. It just eliminates an entire class of concurrency bugs by design.
This leads to this really elegant philosophy, which was famously said about the Go programming language's concurrency model. Do not communicate by sharing memory. Share memory by communicating. Instead of having a bunch of threads fighting over the same piece of data, you have them pass messages to each other. The communication itself is how you safely share information. It completely flips how you think about building these programs.
So how does all of this theory actually come together in the real world? Well, let's take a look at how some of the most popular modern programming languages have taken these ideas to heart to provide what they call fearless concurrency.
Modern languages all have their own flavor. Go is all about simplicity with its lightweight Go routines and those message-passing channels we just talked about. Rust takes a totally unique approach. Its compiler acts like a super strict referee that mathematically proves you don't have any data races before you can even run your code. And then you have Java with Project Loom, bringing these super lightweight virtual threads to its massive ecosystem, making all this high-performance stuff way more accessible. And that really brings us to the ultimate challenge. As our world gets more and more connected, the goal isn't just about raw speed anymore. It's about finding the right tools, the right abstractions to build systems that are simple, correct, and safe. We started out saying that concurrency is a dangerous game played on the edge of chaos. Well, that game is not over. The real question is, how will the next generation of engineers learn to finally master it?